make it easier to visualize, okay, I'm gonna focus on point A. Okay, so here's point A. Pick some other point in the plane. Okay, if you want, you could pick it on vector B, or you can pick it on vector C, but just picture some other point in the plane, X, Y, Z. You could make a vector from A to point X, Y, Z. That vector would be in my plane, right? If this point's in the plane and this point's in the plane, the vector connecting them is in the plane. So this vector will be perpendicular to the one you guys just found. What is true about the dot product of perpendicular vectors? If you find the dot product and your vectors happen to be perpendicular, what's the dot product going to be? 0. Okay? So I'm going to represent this generic vector, okay? That generic vector would be x minus 3, y plus 1, z minus 2. Okay, because how, if you found this vector, how would you find the x component of it? You'd take this x minus this x. How would you find the y component? You'd take that y minus that y. How would you find the z component? You'd take this z minus that z. Yes?
Did you choose to use the A because it was your vertices, or?
I did. It doesn't matter.
It doesn't matter.
You could have picked any of the 3 points. You could pick A, B, or C. I did, though, because I kind of made it the vertex. Okay, so again, x minus 3 is representing the x component of this generic vector, y minus -1, so y plus 1 is representing the y component, z minus 2 is representing the z component of this generic vector. If I dot them, okay, so how do you find the dot product? You multiply the x's together, you multiply the y's together, and you multiply the z's together, and then you add those products, and if they're perpendicular, you should get 0. That's the idea behind finding the equation of a plane. Okay, so I distributed through, and then I'm going to put all the variables on one side, and I will put the constant on the other side, because that's kind of the standard way that you'll see. So, let's see, 17 and -14 would be 3, and 3 plus 39 would be 42, so move it over to the other side, I'll make it 42. So this is sort of my standard form. So what did we basically do? We found a normal vector. How did we find a normal vector? In this case, we took 2 vectors we knew were in our plane. We crossed them because we know that's going to give us a vector perpendicular to them. And then we took the components of the normal vector and we multiplied it by x minus the x coordinate of a point in the plane, y minus the y coordinate of a point in the plane, z minus the z coordinate of a point in the plane. And as Addie was pointing out, I could have picked point A, I could have picked point B, I could have picked point C. If I had picked point B, then this would have been my initial work, which would have given me -13x plus 17y plus 7z plus 80 plus 24 is 104 minus 30. Minus 28 and 34 and negative 28 is 62. And 104 minus 62 is 42, right, yeah, which was what we want. And then when I move that over, you get the same thing. Okay, so, which you should, okay, I mean, it should not matter what point you use, you should get the same thing, but I just kinda wanted to convince you that it doesn't matter what point you use, you should get the same thing once you clean it up. All right, now sometimes you might be doing this and you might get coefficients that are all even, you know, you can divide both sides by 2, you know, you could clean it up further, but, aside from all of these being multiplied or divided by the same constant, the equation of any plane is unique. Okay, so, again, I could multiply both sides by the same number, and hence these would change, but it would create kind of a parallel, parallel equation. So aside from multiplying both sides by the same constant or dividing both sides by the same constant, the equation of any plane is unique to that plane. So let's see, we have